Thermochemistry, Unit 8, Day 1. This is the start of a brand new unit. It's a very short unit, but we're going to go ahead and get started. So before you begin, you will need our new notes packet. No need to print. You can take online notes or you can pick up a packet from Oak Ridge High School. So here we go. The first thing we are going to talk about today is the law of conservation of energy and the process of heat transfer, and we are also going to be classifying reactions as exothermic or endothermic. So this unit is called thermochemistry, but what is thermochemistry? Thermochemistry is just the study of heat changes that occur during chemical reactions. So, when we're talking about our universe, it is made of matter and energy. In recent publications, it is thought that only about 30% of the universe is matter. Matter is anything that has mass and takes up space. So, is everything matter? Let's think about that for a minute. I want you right now to see if you can think of 3 examples in your room that would not be classified as matter. Could you think of anything? I'll give you some examples from the room I'm in. Okay, the first one I'm thinking about is light. You can see the lights in my room. Light is not matter. The next thing I'm thinking of is sound, the sound I'm making right now to record this video, the sound of my squeaky chair. The final one would be heat. If you are in a room that is not freezing cold, that is, you can feel the heat. Especially if you're next to a window, you can feel the heat coming in from the sun. So this is not an extensive list, but light, sound, and heat are not matter. Really anything that is traveling in a wave, such as radio waves, microwaves, infrared light, visible light, ultraviolet light, X-rays, gamma rays, these are considered energy. Anything that will travel in a wave. Now, some of you might have said air, but I want you to remember that air is matter. Air is matter. Air is made up of gas molecules that have mass. Air is matter. Alright, so we're going to talk about the law of conservation of energy. This is a law that states that energy can't be created or destroyed. Instead, energy can move between materials or change form. So, in chemical reactions, all the energy is accounted for as work, stored energy, or heat. You probably have talked about this in earlier science classes, but energy can have many forms. These you've probably heard of: kinetic energy, which is the energy of motion, and potential energy, which is energy at rest. So you can see the person on the roller coaster at the very top is not moving, okay, so they have no kinetic energy, but they have lots of potential energy, this energy at rest. Whereas if you go halfway down the roller coaster, you have some kinetic, some potential, and at the bottom of the hill, you have no more potential energy, but you've used 100% of the kinetic energy. These are all from motion. So that's what you've learned before, but now we're going to kind of change the vocabulary a little bit. Now we're going to talk about types of energy in terms of chemistry. So we're going to talk about chemical energy. This is what you've previously learned as potential energy. Now we're going to call it chemical energy. This is the energy that is stored in chemical bonds. Think about a battery. You're not actually using up that energy yet, but that's a storage place. Thermal energy, on the other hand, is kinetic energy. This is the energy that comes from heat. This heat is generated by the movement of particles within an object. The faster the particles move, the more heat is generated. So chemical energy we're going to use now instead of the word potential, and thermal we're going to use in place of kinetic. All right, so in this cartoon, what is going on here? We've got this lady, and it says, "Breaking news, this heat wave is brutal. Not only is it hot enough to fry an egg on the sidewalk, but you can use your mailbox as a toaster oven." So what is going on here? The cartoon suggests that eggs could be cooked on the sidewalk. Energy moves from the sidewalk to the eggs. So that is an energy transfer. Heat always moves from hot to cold. Okay, so from hot to cold. If you have this ice on a table, the table is giving heat to the water until they reach the same temperature. The table will get that energy, the ice cube will take energy from the table until the table and the water are at the same temperature. So you think about that the ice is making the table colder, but in fact it is the opposite. The table is making the ice warmer. And that is because heat moves from hot to cold. Okay? So that whole process is called thermal equilibrium. Heat will transfer until both objects are at the same temperature. This is why if you leave a glass of water, ice water out or iced tea on a sunny day, all that ice will eventually melt and all the liquid will reach the same temperature. This poor polar bear is eventually going to reach the same temperature as that iceberg he's desperately holding on to. And this is why your coffee or tea in the morning will cool off, because they reach thermal equilibrium. Insulators are really good at slowing down heat transfer, and some nonmetals and materials with air pockets make really good insulators. We have a picture of the pink fuzzy stuff in your attic. That is insulation. That will help keep your home warm in the winter and cooler in the summer. Conductors, such as metals, easily allow heat transfers. Most metals are good conductors. That's why they're really good for making your pancakes and cooking your food. Solids tend to transfer heat better than liquids or gases, and gases tend to make good insulators. Sometimes conduction within an insulator can be sped up with a liquid. So, solids at high density make better conductors compared to gases with a low density. These make better insulators. But we can speed up conduction with a liquid. So in a pool, right, when you are wet, you will lose heat faster than when you are dry. So that is one reason it is much easier to cool down in water. And this ape is doing the same thing. It's a hot day, and you put a towel that has been dampened to help him cool off. All because of that conduction with an insulator can be sped up with a liquid. All right, when we're talking about thermal energy, it can be transferred in 3 different ways: conduction, convection, and radiation. So we see this cloud that's showing convection, warm air rising, the ground heat and in the air, and on our feet is conduction, and the sun heats the ground through radiation. We're going to talk about them a little more specifically. Okay, conduction. Conduction is a transfer of heat through particle collisions. So this is what happens when you're cooking food in a pan. The molecules in the pan will heat up and then they will start bumping into each other, and that speedy molecules colliding will help cook the food. Conduction requires touch for transfer. This does not work effectively in a gas. Why? Because gases are moving so fast they very rarely can even bump into each other. So primarily we see conduction occurring in solids, like these turtles who are warming themselves up on a rock. So conduction, you really want to be thinking about heat being transferred by particles colliding into one another. Convection transfers heat through currents in gases or liquids. So the computer I'm using right now, if the fan wasn't moving, then it would overheat. So it says, with or without a fan, the air in a computer case moves heat through convection. Convection currents form in air and water whenever a temperature differential exists. So for convection, we need a current. Without a current, convection will not occur. Hot liquids and gases are less dense and rise. This causes convection currents. These currents transfer heat throughout the liquid or gas. So we see this fireman crawling on the ground to avoid the smoke and hot air that are rising. And this is an example of convection because that warmer air is rising up and the cooler air descends. So current must be involved. Convection current can only happen in gases, such as air, or in liquids, such as ocean water or lava, not solids. Okay? That is because particles in solids cannot move or circulate. So just like conduction cannot occur in liquids or gases, convection does not occur in solids. Much of the weather here on Earth comes from convection currents. Especially here, we're very familiar with convection because Houston, Texas is a place that gets a lot of tropical weather, a lot of hurricanes and other storms blow in from the Gulf Coast. Places on Earth, the sun will warm the air at the surface of the Earth. The warm air rises and causes winds, and when the air cools, it falls back to the ground. That is convection. So we often talk about heat rising. Heat itself isn't rising, but the air that is carrying that heat will rise. So it's the warm air that is rising, and it's taking the heat up with it. That is why if you have a 2-story house, I bet the second floor is usually a little bit hotter during the summer. Okay, our final type of energy transfer is radiation. And radiation is heat transferred through waves, or the flow of electromagnetic radiation. So, a couple of examples. Heat you feel from a campfire. You're not actually touching the campfire itself, but you can feel the warm heat radiating from that fire. It is the only type of heat transfer that can happen in a vacuum, like in space, and that's how our sun is able to warm up the Earth. The sun's rays radiate through and we can still feel them. Okay, so infrared electromagnetic waves directly from the sun, for example, will hit the sidewalk, the wall, and the person who is standing there. Radiation will transfer heat in all directions. whereas convection currents can only rise. And only radiation will require no contact at all. Convection requires gases or liquids to be present, and conduction requires touch or contact. But radiation can happen without touching at all. All energy on Earth comes from our sun. Space is a vacuum, meaning there's no matter, but radiation can travel through that vacuum no problem at all and heat up our Earth. So we get all that heat energy. So when we're going to study heat changes, think of defining these two parts: the system, the chemical reaction on which you focus your attention, and the surroundings. Your surroundings include everything else in the universe. Essentially, all chemical reactions involve either the release of heat or the absorption of heat. In an endothermic reaction, energy is absorbed by the reaction from the surroundings and will feel cold to the touch. So I always tell students endo has 4 letters, cold has 4 letters. Exo feels hot, exo has 3 letters, hot has 3 letters. And in an exothermic reaction, energy is released by the reaction, and it will feel warm to the touch. So exothermic and endothermic reactions look different on a graph. So in an endothermic reaction, you want to notice that you're always going to start with an energy that is lower, and it will end higher. So you're putting energy into the system. So if you look at the highest point on the graph, it is going to be higher. Look at our energy when we began. It's very low. And by the end of the reaction, it is much higher. So that difference is significant. Whereas in exo, that energy is going out. So it's going out of the reaction. You start with an energy that's pretty high. You're going to end with an energy that is quite low. So if we're looking at them, exothermic or endothermic. Okay, I'm looking at this first one. My energy is low and it's ended more high. So this is endothermic. This first one right here. It's endothermic because it has gone into the system. So that's endothermic. On this next one, this one is my energy started off higher and it ended lower. That's exothermic. Exothermic. On this one right here, my energy started off low, ended up high. That is endothermic. On this example right here, my energy started off low and ended high. Again, that is endothermic. Endo, I've put energy into the system. On this one, my energy started off high and ended low. It is exothermic. That energy has exited. It's gone out. And on this last one, this is endothermic. My energy started off low and ended high. I've put energy into the system. So now we're going to talk about something called enthalpy. We explain this by something called delta H. Delta H. So what does the delta H mean? Well, enthalpy is just measuring the amount of heat released or absorbed in a reaction, and it is given by the symbol delta H. So this is a Greek letter delta, and we read it delta H. For this delta H, we record this by saying H final minus H initial. So delta just means change. So we're subtracting the final reading from the initial. So when we're talking about enthalpy, enthalpies will, for an endothermic reaction, you're always going to see a delta H that is greater than 0, whereas in exothermic reaction, your delta H will always be less than 0. So here's what that might look like. For an exothermic reaction, where the heat is going out, your delta H will be negative because your final, if you do final minus initial, your final is here and your initial is up there. And remember, our formula is H final minus H initial. So your final minus your initial is going to be a negative sign. Whereas in an endothermic reaction, your final is going to be over here, and that's going to be a larger number minus your initial. These ones are always going to be positive. So for an endothermic reaction, your delta H will always be a positive number. And we have another term, activation energy. Activation energy is just the amount of energy that is required to activate atoms or molecules to a condition in which they can undergo chemical transformation. We can calculate activation energy by taking the highest energy reading minus the initial. So here is where our highest would be. If we're looking at our graph, it's going to be at the top minus the initial. So where it began. Highest minus the initial. So typically an exothermic reaction will look like this. There will be our activation energy. And an endothermic will look like this. Now, we're going to switch over to the document camera to look at some of our examples. Alright, so the first place you always want to look at is to see if your energy is being put into the system or if it's exited. So this is where you want to begin looking. I see my energy started off at 45 and it finished at 10. So my energy has exited. So it is an exothermic reaction because it's exited the system. It's exothermic. So to get my delta H, I'm going to take my final, which is 10, my energy final, subtracted from my initial. So 10 minus 45. So my delta H is final minus initial, so that is negative 35 kilojoules. For my activation energy, I want to look at the energy that it took to get up this hill. So that one, sure, your activation energy is your highest minus initial. In this case, my highest point is 103 minus 45. And that is going to be 58. Okay, let's do another example. Okay, for graph number 2, is this showing an exo or endothermic reaction? Once again, we want to be looking to see where we began and where we ended with our energy. Okay, so I began at 50. I finished, ignore the hill because your finishing point is just where it ends, at 100. So final minus initial, your delta H is H final minus H initial. So in this case, we have 100 minus 50, and that is 50. So that is positive. That means this is an endothermic reaction. Right? Anytime we have a positive value, a positive versus a negative, we know we put energy into the system. Endo, think about the word into, right? Put energy into that system. We have more energy than when we began, basically. Now, our activation energy, once again, we want to look at how much it took to get to our hill. So you're going to do your highest, the number at the highest point, minus the initial. So looks like my highest point is 250. So to finish that off, our highest minus initial, we've got 250 minus 50, because that's our initial. So our result is going to be, our result is going to be 250 minus 50, which is 200. 200 kilojoules. Okay. So finally, we've got example number 3. Is this graph showing an endothermic or exothermic reaction? So we want to think generally, is energy going into or exiting? So are we putting energy into this, or is energy gone out? If we look at where we begin and where we end, it looks like the energy's gone down. So it's exo, energy's gone out. And now let's get the specific numbers of how much energy has gone out by doing our delta H. So our delta H is, again, final minus initial. Our final looks to be at about 20. And our initial is 40. So that's going to give me a negative 20 kilojoules. All right, so our activation energy is how much it's taken to get up to the peak. So that is going to be our highest minus our initial. So my highest is 100. My initial is 40. And that is equal to 60 kilojoules. Okay, very good. So that's going to be everything for today, and we're going to see you in the next video.